Cable-stayed bridges are a common type of bridge. Although they resemble suspension bridges, the mechanics behind how they support the structure is different. In a cable-stayed bridge, the cables span out from the towers and connect to the bridge deck. This allows for the bridge to be built in multiple pieces, which allows for easy construction or installation in remote locations. Mathematical theory that has been taught in Math 141 and 142 are used in the design process of these bridges. The main aspect of mathematics required in the engineering of cable-stayed bridges is vector algebra. This is because it is essential to know the forces acting on the towers and the tension in the wires. However, as the geometry of the bridge is 3D, the mathematics required can become complicated. Because of this, we use vectors to provide logical and efficient solutions to dealing with these problems. A vector is a quantity that has both direction and magnitude but not position, for example velocity or acceleration. Vectors as we know them were created in the late 19th century by Josiah Gibbs of USA and Oliver Heaviside of the UK. They created vector analysis to help express the new laws of electromagnetism discovered by James Maxwell. If we know the positions of cables in a cable-stayed bridge, we can create vectors which represent the cables using the formula PQ equals XQ minus XP, YQ minus YP, and ZQ minus ZP. Then, if we assume the bridge is in equilibrium and we know the equivalent weight at each of the tie points on the bridge deck, we can calculate the tension of the cables using the absolute value of TA, which is the tension in the cable, is equal to the square root of XA squared plus YA squared plus ZA squared. Then, to calculate the total force on the tower, we add the vectors. For example, the tension total is equal to tension in cable A plus tension in cable B, and so on. There we have the total tension in the tower. Matrices and differential equations are also used in the analysis of cable-stayed bridges. This analysis is based on the mathematical model which describes the deforming shape of a structure. As the reaction forces of the bridge structure act separately, the overall system is found using the principle of superposition by a summation of the individual action. This differential equation is used to find the bending moment of the beam. In the equation, the function y of x is the equation of the axial deformation, and the function m of x is the bending moment of the beam. This next formula is used to find the matrix of cable forces, which is denoted by the letter P. In the formula, the function m of dx is the bending moment diagram caused by a unit force in cable located at distance dx, and the function md of x is the bending moment diagram caused by a dead load. These formulas allow for the dead load bending moment diagram to be drawn up. This diagram, along with the live load bending moment diagram and the vertical reactions of the elastic supports, are used to draw the resulting bending moment diagram for the structure.